Let's have a brief introduction about general theory of relativity. First, let me recall the Newton's law of gravitation, which tells us the force of gravitation between two masses m1 and m2. Expression of the force, magnitude of the force we can get from m1 m2 capital G by r square. G is gravitational constant, so it's a 6.67 10 to the power minus 11 Newton meter square per kg square. R is the distance between the two masses m1 and m2. If I am standing on earth, I am at a fixed distance small r from the center of the earth. My mass is m1, earth has mass m2. So the force between me and earth is F equal to m1 m2 g by r square. Now m2 is constant because earth's mass is constant, g is constant, r is of course constant because that is the distance between me standing on the surface and on the center of the earth. So m2 g by r square is we can say definitely that it is constant. So the force I am experiencing due to Earth's gravity is F equal to m1 g. G is roughly 9.81 meter per second square. And this is the force with which Earth is pulling me towards its center. And because of the molecular structure of the Earth surface itself, it is so strong that it prevents my fall towards the center. And this makes Einstein to give equivalence principle. Suppose I am in a box, that box is dropped from a very, very high distance, suppose from a Airbus. So I am freely falling. I would feel weightless in this situation. And if I have a ball in my hand and I drop the ball, then I will see rather that the ball is not dropping with respect to me, because the two objects, that is me and the ball, falling with the same rate, and the ball remains still at its own position with respect to me. Now Einstein said that this situation is exactly similar if I am on a box in the outer space. These boxes are, according to Einstein, are equivalent. He further told that what if I am standing on the surface of the earth, I am experiencing this force F equal to m1 g, and this situation is equivalent to when I am inside a rocket. That rocket is moving upward in the outer space and with an acceleration which is equivalent to g. And he said that there is no experiment to distinguish between the two situations. If I am standing here inside a box on the surface of earth, facing or experiencing the pull F equal to m1 g, though I am not falling, and when I am inside a rocket, the rocket is accelerating with a acceleration equivalent to g. No experiments are there to distinguish. I cannot perform any experiment to distinguish between these two situations. I will feel the same. But this is quite not true. There is a little catch. When I am standing on earth, the distance between my feet and the earth is suppose r1, and the distance between my head and earth is r2. So there is a difference of force my head is experiencing and my leg is experiencing, my feet is experiencing, though the difference of this force is very, very small, and this is called tidal forces. For me, I cannot really experience these tidal forces, but those tidal forces are important in the next case. Tidal forces are important in case of water body on earth. The water body which is nearer to the moon gets swelled, we know that. But for us, the effect of the tidal forces is very, very small. Let's get back to the two boxes. On the first box, I am standing stationary on the surface of the earth, experiencing the earth's gravitational pull, though I am not falling. That is equivalent to the rocket which is accelerating upwards with the acceleration equivalent to g, and Einstein said that these two systems are equivalent. This is the equivalence principle of Einstein. But why did he consider these two boxes equivalent? Suppose I am standing on earth, I am stationary here inside the box, I drop something from my hand, and that something, if this is a ball, then the ball is going downward with respect to me. But what if inside the rocket I drop a ball? The rocket is going upward, moving upwards. So, with respect to me, I will see that the ball is still here, but as the rocket moves upward, so the base of the rocket will approach this ball and it will look like this. So for me, it appears to me that the ball is going away downward with respect to me. So the object appears to fall with respect to me, and this happens because the rocket is moving upward. That's why he considered the two boxes equivalent. The same thing happens in case of light. He asked that what happens if instead of a ball I switch on a flashlight, I drop a photon. So here I am switching on the flashlight. The flashlight stays here, my torch, the position of my torch is still here, but as the rocket is moving upward, so this light which is straight here, the bottom surface of the rocket will approach the earth, approach the light beam, and here in the third picture, the bottom surface of the rocket coincides with the beam of light. I will see this as like this. This is my first case where I switch on the flashlight, then it is going upward, so now the flashlight is here now. Again the flashlight is here now. So if I stand here, somewhere here, for me, first the light was here, then it was here, and then it touches the floor. So if I draw it inside one box, so for me the first flashlight was here, then it is here, then it touches the floor and it bends like this. So it appeared to me, the light appears to me to get bent as the rocket is moving upward. So here I get the bending of light as a consequence of the rocket movement with acceleration g. So according to the equivalence principle, the same bending of light will be experienced by an observer on earth, because an observer standing on earth experiencing gravitational pull of earth is equivalent to a rocket which is propagating upward with an acceleration of g. Einstein concluded that light appears to get bent to the observers in presence of the gravitational field. Now, as photons are massless, so how the photons can get affected by the gravitational field itself? Because in the formula of gravitational pull between two objects M1 and M2, masses were involved, and as we know that photon's rest mass is 0. Einstein explained this in a way that suppose there is sun and someone was observing sky from Earth. He or she has observed the sky to be here, but according to the theoretical calculation, the star should be here. So what happens during this total solar eclipse, where Eddington made his famous experiment? It was shown that because of the massive objects like sun, the light rays from this star behind the sun is getting bent like this, and it takes this path. And for me on Earth, or for an observer on Earth, it appears to be here because we follow the straight line path of the light. But bending of light does not mean that speed change occurs, because c is the ultimate speed of light, that is a constant. We know c equal to frequency c, that is speed equal to frequency into wavelength. So c remains unchanged, wavelength and frequency both change, just like the Doppler effect of sound. As the siren appears, as the siren approaches us, that appears to have greater frequency for us. So what happens inside the box in case of light? Suppose this is the box, this is the rocket which was accelerating with acceleration of g. Someone stands here and a photon is shot, and the photon is coming this way. Will it come here at the bottom of the spaceship or the box? The photon will still be here, but as the box approaches upward, it will meet the photon here. So as we can see, it started from here and it meets the floor of the box here. So the wave of the photon, that is wavelength of the photon, is something like crunched, and the crunching of wavelength makes crunching of wave makes the wavelength shorter, hence the frequency higher. So inside the rocket, the wave shrinks, wavelength shortens, frequency gets increased, and as frequency is increased, this is called blue shift, because blue has a greater frequency than the red. Now what happens if someone stands here and he or she switches on light on the upward direction? Will it touch the roof of the box? So as the box is going upward, it started from here, the photon started from here. As the box goes upward, so it hits the rope here, and the wavelength gets stretched the wave gets stretched. So as the box is moving upward, its wavelength is getting broadened, frequency decreases, and as red light has a lesser frequency than the blue light, so this is called redshift. As the rocket is accelerating with g, and according to the equivalence principle, that is same to the observer on Earth. So on Earth, we can also observe the gravitational red or blue shift, and that shift occurs because of the presence of gravitational field. Now let's come to the space-time plot. If velocity is constant, which means x is increasing, like equal increment of time, x increases equally. So if t increases by 1 second, suppose x increases by 2 meter. So for another second, x increases another 2 meter, that is x reaches to 4. And when t is 3, x is 6. For that, we get y equal to mx, that is a straight line plot. So for v, constant speed, we get the straight line. But when the object has acceleration, which means for a small increment of time, x, that is the displacement, increases very much. That is the meaning of the acceleration. For a small time, x increases more. So for a little increment, like when t is here, x is this much. But when t is doubled, for example, x is this much. And when t is thrice, for example, x is here. So this increment is quite greater than this increment. And as t increases further, x shoots up more. So we get a curved line. So an object moving with acceleration, the space-time plot must look like this. And this is the path traversed by object in the presence of the gravitational field. So when we are in accelerated frame, we get a curve through space-time. This is called curved space-time, in other words, according to Einstein.